Hello there. Welcome back to Chapter 1.1 from Stevens' Matrices, Vectors, and 3D Math. This is the second video from this particular section. And before I go to where we left off, I'll just do a brief review of what we did in that first video. So this chapter is dealing with solving systems of linear equations. We defined what it meant for a variable to appear linearly. In this equation, x does not appear linearly, but y does. All right. Then we moved on to systems of equations, where there's more than one equation. And in this particular system, we saw that there was a unique solution. In this system, there were infinitely many solutions. And in this system, there were no solutions. And there's no easy way to tell by looking at them which of these will be the case. And then we saw a systematic way to solve an arbitrary system of equations. That process was called Gaussian Elimination, where you take the system of equations, write it in augmented matrix form, then through a sequence of row operations, you convert the augmented matrix into row echelon form. And once you have your augmented matrix in row echelon form, you use back substitution to solve for the variables. Then we went on to do an example. We started with our system, converted to augmented matrix, did some row operations, worked our way down until we got row echelon form. Then we did back substitution. The last equation gave us x3. The second equation then gave us x2. And the first equation gave us x1. We found a nice, unique solution. And we were able to check that this was indeed a solution, meaning those values for x1, x2, and x3 satisfied all three equations. So we're going to do another example, a similar example, just to demonstrate some more row operations. So suppose we have this system of equations. We're going to first write it in augmented matrix form. And remember, we're going for row echelon form, which means we have ones along the diagonal and zeros below that diagonal. Right? And once we get, if we can get the augmented matrix into that form, we can do some back substitution. So first thing, we want a 1 where that -3 is. Now I could divide that row by -3, but then I'd get 8/3, 8/3. I don't like those fractions. If I can avoid them, I will. In this example, I can avoid them because I can just switch row 1 with row 3. And that'll switch that 1 back into the top position. But notice I'm switching the entire row, not just those two terms. And when I do that, I get my next augmented matrix where I have a 1 in the top left position, which is what I want. Now what I want is to get a 0 where that 2 is. So that's pretty easy to do now that I have a 1 in that first position. I'm just going to multiply this first row by -2, add it to the second row. So 1 times -2 is -2, plus 2 is 0. So I get a 0 down there. That's why I chose -2 as my multiplier. But I have to do this to the entire row. So 3 times -2 is -6. When I add that to 6, I get 0. 4 times -2 is -8. When I add that to 10, I get 2. 3 times -2 is -6. When I add that to 9, I get 3. So it changes the entire row, not just that first term. But I did get my 0 where I wanted it. All right? And so, now, I'm going to go back. And what do I want? I want to get rid of that -3 down there, right? I want that -3 to be a 0. And that's easy enough to do. I'm just going to multiply this first row by 3. and add it to the third row. So 3 times 1 is 3. I add it to -3, and I get a 0. Right? But I have to do this to the whole row, so I take that 3 times my multiplier of 3, which is 9, add it to -8, I get 1. 4 times 3 is 12, add to -8, and I get 4. 3 times 3 is 9, plus -7 is 2. Right. So you might notice I don't really ever do any subtraction. I always take a number, add it to a negative number. I'm not a big fan of subtraction, so I never really use the phrase subtraction. Although when you take 9 and add -7, that's the same thing as subtracting 7. I just avoid that terminology, even though in the symbolism for these row operations you'll sometimes see a negative or a subtraction sign. I'm never really subtracting, I'm always adding negatives. Okay, so that got us part of the way there. We have our 1 in the top left with zeros below it. Now working towards row echelon form, I want to get a 1 there. All right? But I won't be able to multiply that row by anything to get a 1 because there's a 0 sitting there. But fortunately I have a 1 right below it. So if I just switch row 2 and row 3, I'll get that 1 in the position where I want it. So I have my 1 in that second column, second row. That's called the pivot position. These pivot positions keep moving to the right and down. So I've got a 1 in my pivot position there. And fortunately, I want a 0 here, but there's already a 0 there, so there's nothing I have to do. So the only thing I need to do to get to row echelon form is take that 2, and I have to make it a 1. So I'm going to multiply that whole row by 1/2. So that gives me a 1 where my 2 used to be. And then I divide 3 by 2, or multiply by 1/2, and I get 3/2. And once you do that, I'm in row echelon form. Well, I'm not. The augmented matrix is. Okay, so I solve for my variables using back substitution. So if you look at this last row, it corresponds to this equation, which is just x3 equals 3/2. Moving back to the second row, that corresponds to this equation, which I rewrote here, but I already have x3, it's 3/2. So 4 times 3/2 is 6, and I have x2 now. x2 is -4. And then I go working backwards to my first equation. If I write that, it's actually my first row in my augmented matrix. It represents that equation, rewritten here. But I have x2, I have x3. When I plug those values in, they disappear, and I can solve for x1, and I get 9. So there we have it. That's my solution, right? x1 equals 9, x2 equals -4, and x3 equals 3/2. Right? So from now on, instead of writing all of this, the whole idea of this augmented matrix and row reduction is so that we don't have to write all those variables over and over and over. So from now on in the book, and in the answer keys, this first column of involved in the solution process won't be there. And I will also not be including the row operations. You'll just be seeing the sequence of augmented matrices, right? Such as in this situation here. So I give you the first augmented matrix. And you want row echelon form, so you're going to switch these two rows. And that's evident here when you look at row 1 and row 3. All right, so I got to my second augmented matrix by doing a row operation. And in between there I put this tilde. That symbolizes that these two matrices are row equivalent. That means I was able to get from one matrix to the other by one or more row operations. And I don't tell you exactly what they are. It is up to you to sort of figure this out along the way. And that comes from doing a little practice so that you can sort of see how the process goes along. For example, if you got to this augmented matrix and you see we got that next one after some row operations, well, I clearly wanted to get that 2 and turn it into a 0. So I must have taken -2 times this first row and added it to the second row. And that gave us this new row in our augmented matrix. Then if I multiply that first row by -3, sorry, not -3, but if I want to get rid of this -3, right? So I actually multiply this first row by 3, add it to my third row, and I get my new third row. So it's the exact same process. I'm just leaving out some of the details. But it saves a lot of space. And so that's how you'll see these solutions printed out in the book and in the answer keys. Okay, so by the way, it's worth noting, for the first 2 examples, I actually got a solution, right? So I got kind of lucky. I actually got lucky in a few ways, right? So in these first 2 examples, I got lucky in a few ways. Why were we lucky? Well, first off, we didn't have to deal with too many fractions, right? We're doing this by hand. Fractions are going to make this a lot harder. For the problems that I ask you to do by hand, they've been rigged beforehand so that you don't have too many fractions. Future problems that arise will not work out so nicely, but we'll also have software and a computer to help do this process, to solve these systems. We're not completely out of the weeds in terms of doing some stuff by hand, but as far as dealing with nasty fractions in row reduction, we'll be able to take care of that with MATLAB. Okay. The other reason we got lucky is we were dealing with a square system of equations. What that means is that the number of equations is the same as the number of variables, right? So if we go back here, I'm going to scroll way up so don't get dizzy. I started off with this system of equations, right, where I had 3 equations, right, and I also had 3 unknowns, or 3 variables. What that means is it results in a square coefficient portion of our augmented matrix. Right, so that's why it's called a square system. Same number of equations as there are unknowns. The other reason we got lucky was that we were able to obtain row echelon form through a sequence of row operations. You can't always do this. We were able to, in this case, we ended up with this augmented matrix, which was in row echelon form. Sometimes it doesn't work out that way. And when it doesn't work out that way, you're either left with a situation where there are infinitely many solutions or no solutions at all. And the next 2 examples will demonstrate each one of these cases. But before I actually do those, I do want to summarize the types of systems and the types of solutions. Right? Specifically, a consistent system is one that has at least one solution. Right? We have 2 options in this case. We can get a unique solution, as in our first 2 examples. Such a system is called consistent and independent. We can also get infinitely many solutions, and a system that produces infinitely many solutions like that is called consistent and dependent. And then the second type of system is an inconsistent system. Right? An inconsistent system is just that. It has no solutions. Right? And so we've seen 2 cases of this part 1a here, a unique solution, right, which comes from a consistent independent system. So those are the first 2 examples. The next 2 examples will demonstrate the other 2 options, infinitely many solutions and no solutions. And right now there's no way of immediately determining which situation you have. Later, when we start doing matrix algebra with software, there are some tricks we can do to help us determine whether we have a unique solution or not But if we don't, there's some pencil and paper work that needs to be done. So let's do those next two examples, right? So the first of these results in an infinite number of solutions, and that's indicative of a consistent and dependent system. So here's our system, and you look at it, you wouldn't think there's anything wrong with it, so we just proceed with the solution process. We write the augmented matrix. I want to get it to row echelon form by the end of all this. So the first thing I need is a 1 in that position. I don't have any 1s down here, so I can't just switch my way into it. So I divide this first row by 1/2, and that gives me my new first row. The other two rows just come along for the ride. So the next thing I want to do is I want to get a 0 where this 4 is. So I multiply this first row by -4 and add it to the second row. -4 times 1 is -4 plus 4 gives me a 0. That's why I chose -4 as my multiplier. 2 times -4 is -8 plus 5 is -3. 3 times -4 is -12 plus 6 is -6. 9 times -4 is -36 plus 24 is -12. And I have my 0 below my 1. But now I want to get rid of this 2 down here. That 2, I want this 2 here to be a 0. So I multiply this first row by -2 and add it to my third row. 1 times -2 is -2. Plus 2 is 0. That's why I chose -2 as my multiplier. But continuing along that row, 2 times -2 is -4 plus 7. It gives me 3. 3 times -2 is 6. Sorry, 3 times -2 is -6 plus 12 is 6. 9 times -2 is -18 plus 30 is 12. Right? And now I have my zeros below this 1. So I have a 1 with zeros below it. Right? So then I'm going to move to the right one and down 1. And I want this -3 here to be a 1. Right? I can't switch my way into it, so I'm just going to multiply this row by -1/3, or divide by -3. Right? So that takes my -3, turns it into a 1. Takes my -6 divided by -3 is 2. -12 divided by -3 is 4. Right? And my third row just comes along for the ride. So, continuing to head towards row echelon form, I want this 3 to be a 0. So I multiply this second row by -3, add it to my third row. 1 times -3 is -3, plus 3 is 0. But I have to do it to the whole row. 2 times -3 is -6, plus 6 is 0. 4 times -3 is -12, plus 12 is 0. So if I was to continue to pursue row echelon form, I would want a 1 right here. Right? But there's nothing I can do. I can't multiply that row by anything to give me a 1 because there's a 0 sitting there. And I can't switch my way into it either, so I'm stuck here. But if you look at this row and write the equation that it represents, that equation is 0 times x1 plus 0 times x2 plus 0 times x3 equals 0. All right? And that equation is essentially useless, right? It tells us nothing about the variables. Any set of variables will satisfy that equation. Right? So that, when you see this situation, it means that you're going to get infinitely many solutions. Right? But how do I get that infinitely many solutions? Well, I'm going to look back at my second equation, because my third equation doesn't do me any good. And what I do is I get to have a free variable. So I'm going to let x3 be a free variable, right? And to indicate that this is a free variable, I say let x3 equal t. Right? Here t is a parameter. It can be any number, right? And so when I go back to my second equation, represented by this equation here, it's actually the second row of my augmented matrix, is this equation here. But now I have x3, that's my parameter, that's my free variable t. Right? So I get x2 by itself, sub in x3 for t, and I get x2 is 4 minus t. Right, so I have x3, x2, and now I move back to my first equation, or my first row in my augmented matrix, which represents this equation. Right? I solve that equation for x1. x2 is now 4 minus 2t. x3 is t. I make those substitutions. And then I simplify by distributing my -2, collecting my terms. And I can get x1 as 1 plus t. Right? And I'm done with the back substitution process. So this gives us the structure of the infinitely many solutions. Again, it's not just any arbitrary collection of 3 variables. There is structure to this solution. There's just infinitely many of them. And so that structure is given in terms of a general solution. It represents all of the solutions. So x1 is 1 plus t, x2 is 4 minus 2t, x3 is t, and that t can be any number. That's what this represents here. T is any number between -infinity and infinity, right? So we have infinitely many solutions with this particular structure. If I do actually want a specific solution, we call that a particular solution. There are infinitely many. Let's just find one. And the way you usually do that is set t equal to 0. You can set t equal to actually any number you want. 0 is usually pretty user-friendly. So when t equals 0, x1 is 1, x2 is 4, x3 is 0. So there is one particular solution. There's infinitely many that are governed by the general solution given here. Right? Okay, and the final example is a case where we have no solution. Right? It is an inconsistent system. And here it is. Upon looking at it, you wouldn't immediately recognize anything wrong with it that would make it inconsistent. So you just proceed as if you're trying to solve the system of equations. In augmented matrix form, I would like to have a 1 here. I have a 0, but fortunately I have a 1 down there. So if I switch row 1 and row 2, I get this augmented matrix. I'd like to have a 0 here. I already do, so that's good. So I'd like to get a 0 here where that 2 is. So if I multiply this first row by -2 and add it, I get 1 times -2 plus 2 is 0. That's why I chose -2 as my multiplier. -2 times -2 is 4, plus -8 is -4. 5 times -2 is -10, plus 18 is 8. 10 times -2 is -20, plus 11 is -9. And so I got my zeros below that leading 1, and I'm one step closer to my row echelon form. I need now, let's see, I need to go over one row, or over one column, down one row, working to the right and down. I want that term right there to be a 1. It already is a 1, so I'm lucky. So the next thing I want this -4 to be a 0. So I multiply this first row by 4, add it to my third row. 1 times 4 is 4, plus -4 is 0. That's why I chose the multiplier of 4 in the first place. But I do the whole row. -2 times 4 is -8, plus 8 is 0 again. Then I get 3 times 4 is 12, plus negative 9 is 3. And if I was to continue to pursue row echelon form, I would want to make that 0 a 1, but there's nothing I can do to get a 1 there. I can't switch my way into it. I can't multiply that row by any number to convert my 0 to a 1, so I'm really just stuck here, right? But if you look at that row and write it as an equation, that equation is 0 times x1 plus 0 times x2 plus 0 times x3 equals 3. And that should strike you as odd. Right away you'll see there are no solutions. That equation has no solutions, right? You can't take 0 times a number plus 0 times another plus 0 times another and get 3. That equation has no solutions. And so the system of equations has no solution. And we call the system inconsistent. Right? All right, so that wraps up this particular chapter, chapter 1.1. And the key thing to remember here when you're solving systems of equations is that you have a few options. You can get a unique solution, you can get infinitely many, and you can get none. And right now, the only way to make that determination is to just start trying to solve it through the process of Gaussian elimination. You do some row operations, do some back substitution, and if you can get to row echelon form, you'll have a unique solution, and if you can't, then you'll have to work your way through either infinitely many solutions or no solution at all. Alright, so it does complicate matters, and we will develop some tools using matrix algebra that will help speed the process along. But you can't really escape some of the handwork, so it's worth doing these by hand for at least one chapter because it doesn't go away. The software cannot just get you out of this labor entirely. It can help, and we'll get into that in the next chapter. But there is one more video for chapter 1.1, and that is the summary worksheet. I'll go through, there are 3 systems of equations. I'll solve those step by step in the next video. So for now, I will say goodbye.